So then we have step 3. Step 3 is separately fit models for outcome variable y using data with t equals 0 and data with t equal 1. What are these models? The models are, you know about ordinary least squares, right? There is something called weighted least squares. So ordinary least squares was the model that minimized RSS, which was y hat I minus yi squared over all training data points, right? WLS is just another command that you type in Python, and it minimizes a weighted notion of RSS, where for each data point you have a weight. And the weight is the inverse probability weight that says this person should be counted twice, this person should be counted half a time, right? So the model that you fit, actually there are two models. Both of them are weighted least squares. The weights you use are the IPWs, and they become two models for making predictions. And you're going to use these models for making counterfactual predictions for every single individual. Questions? Step 4. Separately make two predictions for, I hope you all can see the board. Separately make two predictions for all data points. So I have a model that I fit using the people who did not participate. This is a model of earnings after 3 years. And I have another model of earnings after 3 years that I fit using the people who participated. Now that I have these two models, for any given combination of values of age, previous earning, and education, I can make two predictions because I have two models. It's only the betas that are different between these models. Otherwise, for making predictions, the weights are not involved. So that's how, in step 4, I'm going to have, in step 4, I'm going to have y hat t for every single individual and y hat u, which means untreated, treated and untreated for every single individual. Questions? So for every individual, I would know the counterfactual, which means what would have happened if what happened didn't happen, if the opposite happened. So then I think some of you may already expect where this is going. Average treatment effect will be the average, so mean, over all data points of y hat t minus y hat u for data points I from the first data point to the last data point. That's average treatment effect, and that allows you to make the causal claim. So as you can see, this was step 0, just to recap. Step 0 takes hours or days. Then the rest of it is, I would say, purely mechanical. You have a Python script. As long as you have the data on the covariates, the rest of it is super easy. And we're going to go through it in Python. We first calculate propensity scores, calculate weights, check for common support, which means overlap of the distributions for propensity scores so that they are comparable, and then calculating balance, which means that the two groups are comparable based on covariates. If balance is not achieved immediately, there's a Hail Mary step, step 2.5, for saving the process. It is not guaranteed, but the idea is that we trim the extreme propensities, hoping that they become comparable enough to pass this step. So if we go back to step 2, check this again. If for all covariates, the standardized differences is less than 0.1, it means that we can continue because the two groups are comparable. So imagine that this is achieved, so we continue to step 3. Step 3 is the first place where Y gets involved. Earnings after 3 years, we didn't use it so far. Importantly, we didn't use it in the calculation of propensity scores. That was just about T as the response variable. Here, we fit 2 different models. These are models of outcome, so models of the outcome variable Y, using weighted least squares for data points with T equal to 0, data points with T equal to 1. Now we have 2 models, and using each of them, I can make a prediction for every single individual. So I make n predictions here, and I make n predictions here. And the difference between these 2 columns for the first row tells me how much the salary of this first person would change based on their participation. And similarly, I calculate the same value for the next person. These are essentially these differences, and the average gives you the average treatment effect, ATE. So why did we do this? Just to recap, because we wanted to make causal claims. Should we always do this for making causal claims? No. This process is an attempt, without a guarantee, for mimicking fully randomized experiments. So in fields where experimentation is the norm, this is not even considered a causal model. But in data science, typically we deal with observational data, and we want to see if observational data allows us to make a causal claim, and that's why we use this. Otherwise, in the best case scenario, this would be as good as fully randomized experiment. And a fully randomized experiment is inferior to the gold standard of experimentation, which is fully blocked experiments. So you learn about those in a course design of experiment, right? But here we're trying to kind of cheat a little bit. We are trying to make causal claims without doing experimentation. So there is no guarantee that this works, but if it works, if we manage to go all the way to step 5, then under 3 strong assumptions, we can make that claim. What are those assumptions? First assumption, our causal diagram is correct, and it captures all the potential confounders. So we're doing this just to get insight, right? It's not about trying to replicate the world of reality. This is just about gaining some insight. That's why we have the notion of all models are wrong, but some are useful. So of course our model will be wrong. Regardless of how many days we spent debating over the causal diagram, we can never achieve a causal diagram that captures all the nuances in the real world, right? But under the strong assumption that this is good enough, this is a close enough representation of the relations between T and Y and other variables involved based on some well-supported justifications. Under that assumption, under the assumption that the models we used are correctly specified, so this is of course a linear model, this assumes that the data generation process is linear, right? Under these assumptions, we can make the causal claim, right? So meaning that the causal claim comes with lots of asterisks and disclaimers. And in a situation where both experimentation and propensity score weighting are available to you, you should opt for experimentation. This is only relevant in the situations where you cannot run experiments. So you may remember when we talked about A/B testing, there was this sort of sanity check that we had for A/B testing. Anyone remembers what it was? Exactly, it was an AA test. So an AA test is just like an A/B test, but we expose the 2 groups into design A. And then we measure we run the test and we see if it leads to a discovery, and AA test, 95% of them should not lead to a discovery. If we run 100 AA tests and more than 5 of them lead to a discovery, it means there is something wrong with the experiment setup. That was the sanity check for A/B testing. We also have a sanity check here. The sanity check is called a placebo test. What is a placebo test? So we do all of these for something for which we know there is no causal effect. So we know there is no causal effect between a treatment in the future and some outcome in the past, right? So let's say we're working with advertising data. You may remember the example with TV advertising, radio advertising, news advertising, and sales, right? So I'm going to, as a placebo test, I'm going to use advertising spending in the year 2022 to identify an effect on sales in 2021. There should not be an effect because we cannot go back, we cannot go back in time, right? If my propensity score weighting method shows me that there is an effect, there's a causal effect from how much we spend on advertising in 2022 on how much we sell in 2021, then there is something wrong with my method. So that's the sanity check. And it's called a placebo test. Questions? Yes?
So, about the common support, so when the distributions of the propensity score between the two groups is distinct enough, what does that imply?
So ideally, we want this. The best kind of the preferred situation is that you see two distributions that very closely match each other. And when this is the case, in the next step, when you try to calculate balance, also balance you will pass the check for balance. So this is desired. And if you start with something like this means that you have to abort. This means that the propensity scores are very different and the two groups are not comparable because those who will end up becoming high earners are those who select into the job training program as if everything was destined, as if, do you know what I mean? As if these were two different populations with two different data generation processes and two different mechanisms. So when I say destiny, I mean mechanisms for what the future holds for them. Yeah. So our model was based on the assumption that participating or not participating makes a difference, and that relies on the assumption that these people could have participated, and the only difference is that they had different propensities for participating, right? Someone had higher education, therefore they would see the ads of the job training more often. They had more disposable income, and they were younger, so didn't feel awkward going there. That's why they had higher propensity participating. So except for the fact that there will be different propensities, people had the chance, right? But when we see this, it means that there was one population that was doomed to never have the chance to participate and eventually being low earners, and there was another population that was privileged to be, high earners of the future, and that's exactly the people who participated.
I was wondering how the arrows that are coming to and from the confounders fit into the whole solution.
So this arrow is always from T to Y. In this example, for this path, the arrows are such that going from T to Y, the directions are respected. That's why this becomes an open door. And since it becomes a front door. Since it is a front door, we don't attempt closing it, which means I'm not going to have a variable recommendation letter here to adjust for it. So this whole process of step 1 to 5 is the process of adjusting for previous earning, education, and age, which are confounders or covariates that give us backdoors. The issue with confounding is backdoor, right? We're trying to close the backdoor so that we identify the effect of T on Y. You may remember the example we had on baldness and extreme outcomes of COVID, right? There was a backdoor for age to represent itself through baldness, right? Here what we're trying to do is to close the backdoors. Because these covariates, right? Sorry, these three covariates impact T, and through T impact Y. That's the backdoor essentially. So that's why when we're going from T to Y, we're disrespecting the direction of the arc, right? And for this one, this was another backdoor because going from T to Y, I'm kind of going opposite direction of the arc here and opposite here. That's why it's a backdoor. And it is a so-called pre-closed backdoor, which means a backdoor that is already closed and you don't need to worry about it. Why? Because of a collider. A collider was a variable to which different variables point to. So the directions, they are very important. They change everything. They change the fact that we ended up with education, age, and previous earning here, and we did this process based on these three, and we didn't have top university or recommendation letter in our data. Other questions? All right, so we're going to see it in Python, and hopefully with the Python example, it becomes more clear. For the Python example, I've used synthetic data. So I kind of played God, and I knew what the data generation process is. So I knew what's the true effect size, and you're going to see that univariate regression doesn't allow us to estimate the true effect size. Multiple regression doesn't allow us, and propensity score weighting, under some strong assumptions, it allows us to quantify something that is very close to the true effect size in the data generation process.